So good morning. Last time we finished with the proposal of de Broglie about every particle, including big particles, molecules, macroscopic bodies, have wave-like properties and associated frequency, wave number, and the matter wave. Okay? So these relations are for free particles. By free particle, we just mean that no force acts on it, so the potential is 0. Okay? And then based on this and the relation between energy and momentum from classical physics, that the energy in the absence of a potential is purely kinetic energy, is p squared over 2m. One can write down a partial differential equation that this matter wave will obey. Okay? And we did that last time. So we just plug in these relations. So this implies h bar omega equals h bar squared k squared over 2m. And so if we want this relation between omega and k, then the simplest PDE that we can write down is as follows. Okay, I'm leaving some space here to generalize this to the case when we have potential. Okay? So just as a reminder, this d dt brings down a minus I omega, which then eats up this I, giving us h bar omega. And the Laplacian brings down 2 powers of k, and we get the dot product of those. Okay? So when v is not equal to 0, the classical formula for the energy is the kinetic energy plus the potential energy. Above, we already accounted for the kinetic energy, so the simplest idea is to add to this v of x. And again, I'm emphasizing this is not a derivation, it's simply the historical route that led people to this equation. This is the Schrodinger equation that governs the time evolution of this matter wave psi. And the shocking thing about this is that this seems to describe nature accurately. So this is a postulate, okay? And let's discuss some properties of this equation. So firstly, last time we were discussing experiments where light was involved, photons, which are massless particles, which do not obey this relation, were involved. But we won't understand the quantum theory of those in this lecture course. That's a lot more complicated, but is a generalization of the formalism that we are going to get familiar with. So this equation is a complex, you can see I here, linear PDE. Okay. So one important consequence of that is that if we have two solutions of this equation, then the linear combination of those solutions, alpha 1 psi 1 plus alpha 2 psi 2, is also a solution. And so what this means is that solutions form a vector space over the complex numbers C. So these alpha 1, alpha 2 can be complex numbers. Because the PD is already complex, it doesn't make sense to restrict to just real numbers. Okay? And often, this vector space will be infinite dimensional. So you can take infinite linear combinations of solutions. And this property underlies the feature that we saw last time that of wave interference in the double-slit experiment. Because we can have a wave that goes through one hole, another wave that goes through the other hole, and then we can add them together. And then we will get this interference pattern. It also underlies much of the philosophical baggage coming with quantum mechanics. Schrödinger's cat that you might have heard about is simply taking a psi that describes a dead cat, taking a psi which describes an alive cat, and adding them together with equal coefficients. Okay? So psi captures wave-like features. So in the absence of a potential, we just get a plane wave. In the presence of the potential, the solutions to this psi will be more complicated, but it's clear that it won't be something localized. It will be spread out in space, and we'll see that it has oscillating features. Okay, so that's good. But then we immediately have the question, but where is the particle? We also saw that particles sometimes behave as particles. Where is the particle? And in our way to abstraction, we somehow lost the meaning of what we are trying to describe, right? We're trying to describe where the particle is, what its momentum, and now we just have this psi, and we don't really know how to extract this information from it. So what does psi mean? And we will answer these questions shortly. Okay? Any question? Okay? If not, then we'll move on to discussing some more general mathematical properties of this equation, and then we will solve this equation for the simplest possible setup, which will be a particle in a box. Okay? So first, we will discuss something called stationary states. Okay? So this is just the physics word for trying to solve this equation using separation of variables. So we solve PDEs by separation of variables. So let's start with the following trial solution. So I'm distinguishing capital psi and small case psi. This one doesn't depend on t. This one depends both on t and x. Okay? And we will plug this trial solution into the equation and divide. So we take the Schrodinger equation and divide it by psi. Okay? And so on the left-hand side, we'll get I h bar t dot. Dot denotes time derivative as usual. And on the right-hand side, we get 1 over psi. And then that derivative and so the Laplacian plus the potential acting on psi. Okay? So left-hand side only depends on time. The right-hand side only depends on x. This is only possible if both sides are actually a constant. And we anticipate that this constant will be energy. Okay? So we just call that constant energy. So this is just the usual philosophy of separation of variables in PDEs. Okay? So let's start with the left-hand side. That's an easy differential equation to solve. It says that I h bar t dot equals Et. Okay? With the solution that t is e to the minus I over h bar Et up to a constant, but we choose to absorb that constant into psi. Okay? So compare this with the time dependence of the de Broglie matter wave, which was e to the minus I omega t. So we indeed recover the de Broglie relation E over h bar is equal to omega. Okay? Compared to de Broglie. Okay? The right-hand side of this equation is a lot harder to solve. Let's write it out. For general V, we do not know how to solve it, but we will consider simple potentials V for which we will develop technology to solve this equation. Okay? So whereas this equation doesn't depend on the setup, this one does depend on M, on the potential, and every detail of the problem. Okay? And we call this the stationary state Schrodinger equation. And we call psi the stationary state. It's stationary because its time dependence is super simple. It's just simply a phase, linear in time. Okay? So just like for any linear PDE, the separation of variables provides an efficient strategy for solving the full problem. So the first step is find all stationary states. So this is a set consisting of energies for which this equation has a solution, and the corresponding psi n's. We will refer to this as nth stationary state. Stationary state. And then, because of the linearity property, and we can add these up, we can obtain a more general solution of the time-dependent Schrodinger equation. So the full problem we want to solve as a linear combination. If we are in a situation where there are infinitely many stationary states, then this sum is infinite. But we don't get scared of the infinite sums anymore. So in most circumstances, and all the circumstances we are going to consider, this is actually the general solution. Okay. And in some cases, we won't discuss those cases too much. This sum is over. So sometimes, most of the time, En are some discrete numbers, but sometimes E is actually a continuous variable, and then this sum gets replaced by an integral. But we won't go there very often. But you can see that in the case of the free particle, any k was allowed, corresponded to an allowed omega. So in that case, actually, we would have an integral instead of this sum. But that's a little more complicated, and we won't discuss it too extensively. Okay. Any question? Okay. So now we are going to solve the Schrodinger equation in one dimension instead of 3 space dimensions. We will just consider it in 1 dimension. And there are 2 reasons to do this. One is mathematical simplicity. We don't want to solve the most complicated problem right away. But it also describes some interesting physical situations. For example, if we have a thin metal wire and analyze how electrons move in a thin metal wire, then effectively they move in 1 dimension. We can forget about the other dimensions in thin wire. Okay. So what does 1 dimension mean? Simply we replace the Laplacian with the second derivative with respect to x. Okay. And we will also focus on the simplest possible potential we can imagine, which will be describing a particle in a box. So Y is a box, a potential. We can draw it like this. So V of x. There's some A. This is the box size. And we model the box with an infinite potential well. So the potential is 0 here, and infinite here, and infinite here. If you go back to your classical mechanics, dynamics intuition, then you will know that classically the particle will just bounce back and forth from these walls and cannot go into the regions where the potential is huge, in this case infinite. So that's why we model a particle in a box with this infinite potential well. So V of x, 0 when x is between 0 and a, and infinite otherwise. If you are uncomfortable with infinity, you can think of this as being some large number and then consider the problem in the limit where that large number goes to infinity. But solving that problem with a finite v would be a lot harder, so instead we just consider the limiting case. Okay? So why are we happy about this potential? Because it's piecewise constant. So the Schrodinger equation, if we solve it inside and outside, will be very simple. It will be on the right-hand side, we will just have a second-order differential, second derivative in x. Okay? So I said that classically we have this bouncing back and forth with constant momentum. So P is plus minus P. P is just the norm of this one-dimensional vector. And the energy is only kinetic energy is P squared over 2m. Okay? In particular, for any value of P, we get an energy. So energy is continuous. We will see that quantum theory makes the energy discrete. Okay. So we want to do quantum theory. So first, let's write down the Schrodinger equation, actually the stationary state Schrodinger equation inside. Okay. Up to these annoying factors, it's really just psi double prime of x. So prime is the space derivative in my notation, and dot is time derivative, is e times psi x. We know how to solve this equation. We will write down the solution in a sec. Outside, we have a term in the equation which is like infinite times psi equals something. Okay, so one way to satisfy this equation, and in fact the correct way to satisfy it, although what I'm explaining is not very rigorous, is to say that psi of x is 0 outside. Okay, so this is inside, outside. So it acts like, and so we consider psi that is continuous and continuously differentiable, so that the second derivative makes sense. And with this boundary condition that at the end of the box, psi has to go to 0. Okay? So this becomes a boundary condition. Question? Okay. So let's start with assuming that the energy is greater than 0. So we have the equation psi double prime is E times psi. We solve such linear ODEs with constant coefficients with exponential trial functions. And so it's easy to see that what we get is a plus, a constant, times e to the I over h bar square root 2 me times t. And we can also get it with the other sign, a minus e to the minus I over h bar, same thing, e. Okay? Because if we act, oh, wanted to write x, sorry. If we act twice with the derivative on this, it brings down 2 powers of this, so the sign doesn't matter, and this squares to 2m e over h bar squared. Okay. In the lecture notes, this problem is solved a little differently. I chose to present it this way so that you have 2 perspectives. Okay? So you may be more used to solving this equation as either linear combinations of sines and cosines or sinches and coshes. Here I'm doing it with complex exponentials because complex functions will be prominent in this lecture course. Okay? So that's good. So in particular, these functions make sense for any value of e. So where does discreteness of the allowed e's come from? It always comes from boundary conditions. So what are the boundary conditions? That when we get to the wall of the box, the wave function has to vanish. So psi of 0 has to be 0, and psi of a has to be 0. Okay? So let's plug in x equals to 0 here. This says that a plus plus a minus is 0. And so this leads to, let's say, a minus equaling minus a plus. And now we can plug x equals a in here and use this relation to get a plus e to the I over h bar 2me a minus e to the minus I h bar square root 2me a. And in here, you recognize sine, right? So this is 2I sine of the argument. Okay. So you see that for generic E, this equation is not satisfied. But there exists a family of E's for which this is true. Okay, so this determines the allowed E's. So what are the allowed E's? We need sine to vanish, and so it needs to be an integer multiple. The argument needs to be an integer multiple of n pi. Right? Okay, and so this is true for any n in Z. But note that that if n is 0, then we have n is 0, E is 0. So we just get the 0 function. So we don't like that. We will discuss why we don't like it, but that's always a solution of a homogeneous linear differential equation. So we just discard that. And for n negative, we get the same solution up to a relabeling of what A plus and A minus means. But since these are arbitrary constants and we can multiply with arbitrary constant a solution, it's still a solution. We only get distinct solutions for positive integers. Okay? Yeah, so, okay. So you will see this more clearly when we actually write down the wave function in a sec. So the allowed energies are labeled by these positive integers n, 1 over 2m, h bar, n pi over a squared. I'm writing it this way because you can recognize that this thing is what we call k, the wave number of a plane wave. So you see the relation energy is 1 over 2m times momentum squared pop out from here, and it's the fact that these k's are only allowed to be certain values to satisfy the boundary conditions. So we have the relation P, the momentum is h bar k, and the energy is p squared over 2m. Okay? So I can write this as Pn squared over 2m, where Pn is h bar kn. Okay? But if you don't care about this, then this is just the formula. You can just do the square, simplify it however you want. Okay. So for n equals 1, we get the lowest energy stationary state with energy greater than 0 at least, and we will call this the ground state of the system. Again, this is just the stationary state for which the energy is the smallest. Okay, I jumped a little bit ahead, so we didn't really consider seriously E smaller than equal to 0 yet, although this formula can also be used for negative E. But in more detail, for E equals to 0, the solution of the equation, so it's just psi double prime is 0, so that's a linear function, A plus bx. this constant is killed by the boundary condition at 0. So this has to go. Then we are left with this, and this is killed by boundary condition at A. So this also has to be 0, so the whole thing has to be 0. And I told you that we don't care about the 0 solution of this equation. We will see why in next lecture. And for negative E, we have, so if we satisfy, we can use this formula, and so A minus equals minus A plus will be true, and then psi of x wants to be a sinh. Maybe let me absorb a factor of 2. So it wants to be a sinh of square root 2 m e absolute value over h bar squared times x. So this satisfies the boundary condition at 0, but it doesn't satisfy it at A. So this again doesn't work. Okay, so now it makes more sense to say that the lowest positive energy solution is actually the lowest energy solution among all the ones that are actually solutions. Okay, and then for n equals k plus 1, we call those states the kth excited states. And again, this is just some physics language, but the content of it is that if we, let's say, shine light on the ground state, it absorbs a photon of appropriate frequency, then it can jump, get excited to a higher energy level. Okay. So somehow I didn't write down, yeah, okay. To be more explicit, let's just write down what the psi's are. Okay. Okay, sorry. Yes. Okay. So first, let's just say one more comment about this photon absorption or a transition from the transition from the excited state E2 to the ground state E1. Okay. So this is related very crudely to what we described with the hydrogen atom spectra, emission spectra, in the first lecture. So let's look at this transition. By energy conservation, the photon energy that comes out of this transition is E2 minus E1 equals h bar squared pi squared 2ma squared. So I'm just using this formula, and then I'm plugging in n equals to 2 and n equals to 1 into this formula. So that's 2 squared minus 1 squared. That's 3. Okay. Now, if we plug in the mass of the electron in here, which is a small number, it's 9.1 times 10 to the minus 31 kilograms. And we also need to, so we talked about what h bar is. That's also a super small number. What we need in addition is some size of a box. We're trying to model our hydrogen atom with a one-dimensional box. It's extremely crude, but that's what we can do at the moment. So it's reasonable to plug in for A, which is some distance, the size of an atom. So that's 10 to the minus 10 meters. Okay, so you plug in these numbers, and you get that this transition is 1.8 times 10 to the minus 17 joule. Okay, so this one photon wouldn't heat up your room, This is very minuscule energy, but we can convert it to wavelength. So we have energy, then we can convert it by h bar omega to frequency. And we had that relation last time, that how to convert omega to wavelength. If I use that, I get that this is 1.1 times 10 to the minus 8 meters, so 10 nanometers. That's actually the correct order of magnitude for the second to ground, so first excited state to ground state transition in hydrogen. So this is indeed, like visible light is around like 500 nanometers. This is a little shorter than that, but it's in the good, nice ballpark. So even this very crude thing gives some promising result. We are working with extremely small numbers, but they combine out into something reasonable. Okay, and so let me summarize what we got, because I realized that I didn't write down the wave function explicitly. Let me do it here. So summary. So we are constructing an elementary set of solutions to the time-dependent Schrodinger equation. The time dependence is simple, t, and then this is multiplied by the stationary state, which is x-dependent. Okay, so for our problem, we determined these stationary states. There's some overall normalization. I will write down what the actual formula for E is. So it's minus I n squared pi squared. In the numerator, we have an h bar squared, but we have an h bar in the denominator, so we get an h bar up here, 2ma squared times t. And what is the spatial part? So this is what I forgot to write down when we were discussing. So n pi a over x. And probably this is the place where we see that negative n is equivalent to positive n. Because if let's take n equals minus 7, that's the same thing as the solution for minus n equals 7. But because this a is arbitrary, I can just absorb that minus sign into a. So I'm good. Okay, so this is inside. And outside, we argued very hand-wavingly that the wave function should be 0. This is where we got the boundary conditions from. And so this is why the sign has to vanish both at x equals to 0 and x equals to a. Okay? And just to drive the message home, so this is some basic solution. The general solution is obtained from taking any linear combination of such psi-n's. And it may be that you need to take an infinite linear combination, but you're already used to it from Fourier analysis, like Fourier series, right? These are just Fourier series on the 0 to a interval. So at every instant of time, we just have a Fourier series problem. And then they get multiplied by phases that change linearly in time, but at different rates. Okay? And one more physics terminology, that this n, which is just a label on the solution, is often called a quantum number. It's very hard to define what a quantum number is, but when you see one, you will recognize it as a quantum number. Okay. So we solved the Schrodinger equation in the simplest possible setup, and we saw that we get discrete energy levels in stark contradiction to what we get classically. where any energy was allowed. So that's another feature of quantum theory that we discussed last time, and we're already reproducing it just by solving an ODE problem. Okay, any question? Okay, if not, then we will discuss a slightly more complicated problem, this time in 3 dimensions. Okay, so 3D box. Again, how do we model a 3D box? We model it by the potential, which is 0 inside. So what do I mean by inside? I mean that x, the first coordinate, has to be in 0a, y has to be in 0b, and z has to be in 0c. And if either of these is not satisfied, then we have infinite potential outside. Okay? So what's the stationary state Schrodinger equation inside? Again, where do I have it? Sorry. So we just have to solve this problem with v equals to 0 inside. So it's just a Laplacian acting on psi equaling E times psi. So what's the Laplacian? I'm multiplying the whole equation with minus 2m over h bar squared to cancel. So the left-hand side is simply the Laplacian. Dx squared, dy squared plus dz squared, right? That's the Laplacian Cartesian coordinates acting on psi, which now is a function of all the 3 coordinates x, y, z, has to be equal to E times psi. So this is inside. And we also need to supply this differential equation with boundary conditions. And it is that psi equals 0 at the walls. So whenever we reach x equals 0 or x equals a, and similarly in y and z, then psi has to be 0. Okay? So this is to solve this PDE. So even though we got rid of time, we still have a PDE at our hands. So we did one separation of variables, but that's not enough. We again have to use separation of variables to solve this equation. Okay, that's a problem on the problem sheet. So you will solve it at home. But the solution, so the outcome of this will be quite easy and intuitive to follow. So this is in problem sheet 1. We get, so the outcome of this procedure is that we get a stationary state labeled by 3 positive integers. And the stationary state wave function is simply the product of 3 one-dimensional stationary state wave functions. So sine n1 pi over a x, sine n2 pi over b y, and sine n3 pi over a z. Okay? So this is inside, and outside we see that it vanishes. At least at the walls it vanishes, and then we can take them to vanish even outside. Because each of these signs has the property that it vanishes at the walls. Okay? And what's the energy? The energy is simply the sum of 3 one-dimensional energies. h bar squared pi squared over 2m. And we have n1 squared over a squared, n2 squared, b squared, and 3 squared, c squared. Okay? Okay? So I think this is quite plausible. If you do separation of variables, you will get 3 one-dimensional problems. You solve them, and this is what you get. Because the energy, so maybe this one needs a little explanation. So n is a vector now, 2m. But if we write this out, this is h bar squared over 2m. And then we have, kx and 1 squared kx y and 2 squared kz and 3 squared. And these k's are what you find in the argument of the sign. Just like in dynamics, you are familiar with that in the three-dimensional motion on the plane, you can get the energy by adding up the squares of each momentum component. Okay. There's something remaining from this lecture. So we'll discuss one more aspect of these formulas, and that will lead us to the end of this lecture. And it's about degeneracy. Again, a physics term, you will get used to it. So we saw that the full Schrodinger equation, the time-dependent one, has the property that I can add together alpha 1 psi 1, which is dependent on t and x, and alpha 2 times psi 2. But the stationary state Schrodinger equation, while it's also a linear PDE, it's not true that I can just take two stationary states, one corresponding to one energy, the other corresponding to the another energy, add them together and get the solution. That just doesn't work because the equation changes. E enters the equation. So this is nonsense, what I'm writing, and I'm going to cross it out in a second. So this is a solution of nothing. Or probably you could cook up some equation that it solves, but it's not the solution of any thing relevant. So this is nonsense. But it may happen. It didn't happen for us in the 1D box. But it may happen that that there are multiple solutions to the stationary state equation, linearly independent, for the same energy. And then you can add them together. Then they form a vector space. Okay? So then the most general solution of the stationary state equation at that energy is the sum over I from 1 to some number d, which is an integer and is what we call degeneracy, some ci, coefficient psi I, at that energy. So this is a vector space C to the d, vector space of solutions. And the psi I are the basis vectors in this vector space, and the ci's are the components. So these basis vectors, because they are linearly independent as functions, and these are the components. This is just a preview. We're going to discuss the structure of this vector space in a lot more detail later. Okay? So, let me leave this. Okay. So the 3D box is important for us because it's the first example which provides such a circumstance. So in 1D, all energy levels are non-degenerate. So that means that D equals 1 for them. Degenerate. In 3D, this is also true generically. But if we take A equals B equals C, this is a non-generic value of parameters, right? It's very unlikely if you just randomly chose A, B, C to get this. Then this formula simplifies to something that will clearly have degeneracies. So this is n1 squared, n2 squared, and 3 squared. For example, let's take the energy level h bar squared pi squared over m a squared times 3. The values of n1, n2, and 3 that produce this are 2, 1, 1, 1, 2, 1, so all permutations. 1, 1, 2, all give the same energy level, but the corresponding size are linearly independent. As you can see, because in the argument of sign, you will have just different numbers. So those are linearly independent by what you learned in Fourier series. Okay, and with this, I'd like to thank you for your attention.